So now we're set to begin talking about looking at variability when the data comes specifically from a sample. So we'll look at how we do our variance and standard deviation a little bit different. And really it's almost all the same. There's one small difference, a very important difference, but one small difference. So we want to get our variance for our sample. Let's use the same scores that we had up here before, just for ease. All right, so now this is data from a sample. And I know this doesn't represent the full diversity. There are scores that were probably higher than a 5. There may have been scores lower than a 1. Winter temperatures in Minnesota, right? We can definitely get some negatives could have come in there, right? If we had some interval level data. So anyway, I know that this is the diversity represented in my sample, but my sample is supposed to be representing the population that has even more diversity than what I can see here. So I'm going to make these adjustments to sort of expand the results I'm going to get. Make them, again, a better estimate of the population variance. Well, the first thing we need here is a symbol. So since we're dealing with samples, then our symbols are going to be letters from our own alphabet. So for population variance, it was a lowercase Greek s. So for us, we're just going to use our own little lowercase s. And again, with the exponent on it. Sample variance is the exact same definition as population variance. Variance is variance. So sample variance is the average squared distance of raw scores from the mean. Same diff. So we need to do it in 2 steps, just like before. So our first step is to get the sum of squared deviation scores, or sum of squares. Pardon me, same symbol, that's not different. SS for sum of squares. And the formula here is the same. We're going to change one of the symbols to represent a sample instead of a population, but the math is the same. So it's the summation of the squared raw scores minus the summation of raw scores squared over the number of raw scores. So we just change out the capital N for a lowercase m, but mathematically it's exactly the same. And since we have the exact same data here, we already know what the answer is. The answer is the same. The sum of squares for this data was 10 points. You can recalculate it if you'd like, but you don't really need to. It's the same data, it's the same formula, so it's the same answer. So the sum of squared deviation scores is 10 points. That's the same. No, computationally, no difference. The difference comes in step 2. So sample variance is sums of squares divided by the number of raw scores in the sample minus 1. We're not going to take the full number. We're going to reduce it by 1. This idea of n minus 1, number of scores minus 1, is called degrees of freedom. It's a somewhat abstract concept. Definitionally speaking, degrees of freedom tells you the number of scores in a set that are independent and free to vary. It tells us the number of scores in a data set that are independent and free to vary. And we can see that that's all of them but 1. All the raw scores except 1, minus 1, are independent and free to vary. It's kind of an odd concept for a lot of folks. Let's think of it this way. Let's say 3 of us are going to get together and we're going to empty out our pockets and put all our money on the table. So I empty out my pockets and put some money out there, and you do, and another person with us does. And we add up all the money, and there's $20. We add it all up and it's 20 bucks. So I ask you, how much of that money was yours? And you say, $10 of it was mine. It could have been anything. You could have said none of it. You could have said $20. You could have said $10.50. You could have said $15. You could have said $3.12. It doesn't matter what the other answers are in the moment. It's independent. It's free to vary. It could have been anything. But it turns out that it was 10 bucks. So you say, well, $10 of that was mine. And then I go to the next person and I say, well, how much of that money was yours? Their answer could basically be anything, but they say, $7 of it was mine. If $10 of it was yours and $7 of it was his or hers, and there's a $20 total, well, we know how much of that money has to have been mine. My answer is completely dependent on all the other answers. My answer is being defined, is being fenced in based on what all the other answers, based on what all the other data is. Mine isn't a mystery. Mine has to be $3. 17 is the other folks, and it has to add up to 20, so 3 is the only thing that's left. So all the answers out of these 3, 2 of them were independent and free to vary. Could have been anything. All but one of them, that last one, was locked in by the other answers around it. That's what degrees of freedom is about. Why it's important here is because we're reducing the size of the denominator by a point. When you're dividing, the smaller the denominator, the larger the quotient, the larger the answer will be. Divide something by 100, divide something by 10, you get a bigger answer when you only divide by 10. So by reducing the size of this denominator by just 1, what we're going to do is divide a smaller number into that numerator, and it's going to do what? It's going to inflate the answer. It's going to adjust that answer to be a better estimate of the population it came from. Because remember, this isn't a population anymore. We know we're missing scores that might be higher or lower than what we see here. So what we do here is the same simple division, but we're just going to make that little correction. So our sample variance is our sums of squares was 10. And the number of scores was 5, but we're going to subtract 1 off of that. So now it's 10 divided by 4 instead of 10 divided by 5. Well, let's see what happens here. 10 divided by 4 equals 2.50. Again, remember our classroom procedures. If your answer has a decimal, it must be written to 2 places. All decimals are consistent. 2 places, 2 places, 2 places. Well, let's think about that for one quick little second here. When this was a population, we said that's all the data there is and nothing is missing. We don't have to make any adjustments. Our variance was 2. But now we're saying, look, these 5 scores are just a sample. We're missing part of the picture. We've got to make an adjustment here for some of the variability we're not seeing, for scores that might be higher or lower than what's being presented here. So we are going to inflate that measurement. So we pumped it up from 2 by making this change in the denominator up to 2.5. The idea is that this 2.5 is the sample variance, and it's meant to provide a better estimate of the population it represents. So that is our sample variance. So same 2 steps. Step 1 identical. Step 2, only thing we change is the denominator. Now the risk here is that students get carried away and they start subtracting 1 off of everything. They go, oh, it's a sample, and they start subtracting 1 off of this end. Anywhere they see a lowercase n, they're just like, chip a point off of it. It only happens in one spot. We don't correct it here and here. We'd be overcorrecting at that point. We only correct it in this one spot. So step 1 is identical sample and population. Step 2 just has that one tiny but crucial change that we have to pay attention to. So from here then, we can move forward to talking about computing standard deviation for the sample, but we'll need to pick that up in the next clip.